Welcome, everybody, to the Playing Games podcast. And today I'm joined by a very special guest, Dr. David Behm. Dr. Behm, how are you doing today?
Not bad. How about you?
Good, good. Thank you again for allowing allowing us to have some of your time for a podcast, because you seem to be very involved in the exercise science field. And a lot of your work seems to be thrown around in the social media space. So I thought it'd be very interesting to have you on here, so maybe you could elaborate some of that work and your expertise in the field as well. So thank you again for your time here. Before we get started, I'd always like to have the guests introduce themselves a little bit. So if people haven't heard of you, or if they have, but they like to know a little bit more about you. So if you could just introduce yourself a little bit, your experience in the field, your current work, your past work, things like that.
Sure. So first of all, my name's David Behm. It's an A
Oh,
sound. I know there's only four little letters. I've been called Behm, Behum, but for some reason it's Behm, and so Behm like fame, like name. So I'm a university research professor at Memorial University of Newfoundland. I've been here for 30 years. I've been publishing. My first publication was in 1991 in a scientific journal. I did some training type publications back in the 1980s with like the Strength Conditioning Journal down with the NSCA. So I've been at this for over 30 years, and I've always been really interested in sports science because I was an athlete. I played as a kid. I played baseball, hockey, and football. I was drafted into the Canadian Professional Football League, but I only lasted 1 month and got cut. So I had a very short career, never made it to the Football Hall of Fame. And then after that, once I got cut from football, I had to find something else to do. So I started playing tennis. I played squash, won a few provincial championships doing that. So I've always been a highly competitive athlete. And anything I do, I want to compete. I don't do things just for fun. It's not part of my nature. If I'm doing something, I want to win at it. So, and then if I'm not that good at it, so like I say, I didn't make professional football, then it interests me how to improve, not only myself, but others. So my first big area was velocity specificity of resistance training. And of course, that was my big fault as a running back was, I didn't run the 40 in 4.4. I was, fairly slow for a professional football player. So I wanted to see, how do people, become better? Another area I looked at was like instability resistance training. And again, it's an area that people picked up in the early 2000s and started doing exercise on Swiss balls and Bosu balls. And again, I was thinking, well, the concept of training specificity applies here because you're playing on a field that could be slippery, or in my past as well, hockey on ice, etc. So I looked into that, and then of course I did stretching a lot as an athlete, and then there was a controversy about it causing impairments. So over the years, I've been very curious about everything that has to do with athletic performance and athletic success.
that's awesome. I mean, and we're going to touch on a few of those topics today. We can go over most of them. So it seems that you have experience not only behind the research, but also in the actual field. Have you ever trained anybody? Were you ever a trainer of some sort to athletes?
Yeah, quite a bit. So I was after my football career as a player, I was a football coach at a small university in southern Quebec in Canada. So it was called Bishop's University. So I was the running back and wide receiver coach and the strength conditioning consultant for them. I ran an athletic club in Nova Scotia in Canada, and we had a weight training facility there. So again, I was involved in training with those people. I could name off a whole bunch. I guess the big highlight would be in 2006. Actually in 2005, one of the curling clubs, curling teams in Canada, one of the best ones in Canada, the Gushu team, came and asked me for training advice. And they ended up winning the gold medal in 2006. So I did a lot of work with them in terms of instability training, because again, I'm sure not everybody in this podcast knows what curling is, but that's when you're throwing these big granite rocks down the ice and trying to fit. It's like a game of what am I trying to think of? I can't remember the name. You might play it on a boat, and
The
you
cruise ship
push.
game,
Say again.
on the cruise ship where they kind of get like the puck and they slide it on the wood,
Yeah,
something like that.
except in our case in Canada, we're very good at doing that on ice with rocks. So we won the gold medal, and I'd help them. So again, so I have a practical background, both as an athlete and a coach, and then of course I've got the academic research side of things.
Yeah, and I think that's a very, I think, important for researchers in general, because sometimes if you're always behind the lab, you kind of see results and outcomes of papers, but then when you try to apply them into the real world, there are just some things that science isn't there yet to explain, or that doesn't apply into like a one-on-one relationship. You mentioned instability training with the athletes. Just to touch on that a little bit, do you mean you train them a lot on Bosu balls and things like that? Because I know there is some contention about the idea of stability training. They're like, well, if you can squat really heavy, you can naturally kind of just do a Bosu ball with a bit of a practice. So do you really need instability training, or are there certain cases where it can be helpful?
Absolutely. So as usual, there's no one answer to anything. If you're a scientist, you kind of find that out. So you're absolutely right. We've done research where we had people doing chest presses on Bosu balls, and their forces dropped by 60%. So it's a major drop in force. So if you're an elite athlete and you want to get stronger or gain hypertrophy, you're not going to achieve that if your maximum forces are 60% lower than they could be. And you're right. If you do squats, you do deadlifts, you do a variety of different activities. It inherently has a balance component to it. You're sticking, well, however strong you are, 100, 200, 300 pounds in your back. You got to really work on your balance to lift that up. So athletes tend to have good balance because, like I said, doing squats all by itself improves your balance. But what if you're not an elite athlete? You don't want, to go to the Olympics. You don't want to be a professional athlete. You just want to lift weights for health, and you're actually afraid of lifting heavy weights. You're afraid you're going to get yourself injured. Well, the good news is that even when you lift lower weights or lower loads when you're unstable, your muscle activation is still high. Because everything's unstable, then your joint stabilizers have to be activated. You tend to co-activate, so turn on the agonist and antagonist muscles to a greater extent. So you get this high activation with low loads, and so you get a healthy stimulus to the muscles, which will still make you somewhat stronger. You're not going to go to the Olympics. You're not going to play professional football or hockey by doing that. But still, if you want to go in and you want to lift lower weights with high activation, it's great. And furthermore, what if you are an elite athlete and you just got injured? And so now you injured your shoulder, you want to do some sort of press. Well, you can't do very much in terms of load. And then, of course, the activation is low. So your rehab is really slow. But if you are doing it unstable, you use low loads, but high activation. So elite athletes, it can be good for them for rehab, and for the general population, if you're not interested in lifting big weights, you can still get high activation with doing things under unstable conditions.
It's nice that you bring that up of co-activation and activating multiple muscles at the same time, because right now there is some debate about whether doing things like single joint movements or unstable movements is better for building muscle of some sort, because or training muscles, because when you, let's say, do an exercise that requires a lot of different muscle groups or very large muscle groups, there is, I believe, some work from yours and other people as well, that there is this reduction in voluntary activation, the voluntary activation deficit. So people now would kind of suggest, well, look, let's try exercises that are more single joint or more stable, that have more stability to activate more motor units, rather than doing unstable exercises or exercises that have multiple muscle groups, because if we have multiple muscle groups activated, it will be hard to fully activate those muscle groups or target muscles. If that makes sense.
Well, yeah, it certainly makes sense. So, what's your goal? Well, if your goal is to get a bigger bicep, and you don't care how you use it, you just want to go to the bar and have this big bicep that you can show off. Well, yeah, and just do unilateral movements, and you get high activation, and you can throw under stable conditions, throw high loads on there, and you can wear your tight shirts and go to the bar and look great. But if you're an athlete, you want that bicep to do something, or that tricep. And normally, the biceps and triceps aren't working on their own. They're working with your deltoids and your pecs and your lats. And, you've got to coordinate all your upper body. And again, with the athletes, typically the forces begin in the lower body, and then you transfer them to the upper body. So even though you're right, we published an article years ago showing, of course, that multi-articular movements have lower muscle activation than uni-articular movements, because your brain's job is to focus and get down there and then activate those muscles. Well, if you have to activate 5, 6 muscles, or who knows how many muscles compared to one muscle, it's going to be more difficult. But that's the point. When we're hitting a hockey puck, throwing a football, making a jump shot, whatever we're going to do, we've got multiple muscles working together. And so we got to go into the weight room and teach the body how to activate at a high level with multiple muscle groups. You're not going to teach the body how to do that by doing unilateral bicep curls.
Do you think with enough training, let's say in those papers that you've published, because I mean, studies have limitations. So if you have, I don't know if you used trained or untrained lifters.
In that one that I was just speaking about with the multi-articular versus uniarticular, they were just active individuals of university student age.
Okay, because I would think, especially with just resistance training in general, as you train, your body gets better at neuromuscularly, right? Becomes more neuromuscularly efficient. So do you think it would be able to learn to recruit more of the various muscles that were recruited in multi-joint movements or unstable movements per se, rather than just saying there's only this deficit in activation, but that deficit can't increase over time the better you get at the movement?
Absolutely. So yeah, that's what you want to do. So, for instance, under unstable conditions, there's a thing called the stiffening strategy. A stiffening strategy is when your body, let's just put it in easy vernacular, is afraid that you're going to get injured. So you're, standing on a Swiss ball or a Bosu ball. Just imagine that you had this 2x4 piece of wood, and it's on the floor, and you're supposed to walk across it. Well, if it's on the floor, you just go and go very quickly. But now stick that 2x4 between two high rises, 20 stories high, and ask the person to walk across them. Well, now they're going to stiffen up because they're afraid. And so what's going to happen if you have them become familiar with that movement? I'm not proposing that everybody go and try and walk across two 20-story buildings, but doing squats or doing Olympic lifts or doing plyometrics or whatever, once you get accustomed to that, then the fear goes down, the stiffening strategy goes down, so there's not as much co-activation. The antagonists aren't inhibiting your movement. And then as well, you've got all these inhibitory agents in your system. So you've got interneurons. When you're doing antagonist contractions, you've got that thing called reciprocal inhibition. Contract the antagonist and it'll inhibit the agonist. You've got recurrent inhibition with Renshaw cells. I could go on, but you learn how to turn those off. So what the term would be, you inhibit the inhibitors. So if you've got all this inhibition, you want to turn that inhibition off to allow the excitation from your brain to turn those motor neurons on when you're doing more complicated movements, like multi-articular or under unstable conditions. So you definitely will, over time, be able to improve motor unit recruitment, motor unit rate coding or firing frequency, et cetera, et cetera.
So essentially the brain learns to use the muscles that are being used for the task more efficiently without having the need to recruit unnecessary or muscles that could be inhibiting the task itself.
Absolutely, you got it.
I heard I heard the saying before saying that you can't shoot a cannon out of a canoe, kind of like saying that
Yeah,
um,
you either saw one of my presentations or you saw it online. Yeah, so I use that in my presentation, and I have a picture of these pirates in a little canoe with a big cannon. And so what would happen if you shot that cannon? Well, in a little canoe, the canoe falls right over, and you're stuck in the water. So it's ineffective. You need a foundation. You need a core, a strong core. So then what I next show is a picture of a great big battleship. I always make fun of Canadian Navy. I said the Canadian Navy is the canoe and the American Navy is the big battleship. But nonetheless, the big battleship, it has a huge foundation. It's got, one might say in physiological terms, it's got a strong core, and you can fire off these great big cannons. So then what I say is, these are your cannons. You can't fire these cannons unless you've got a strong core and a strong foundation, which is your obviously your lower limbs, legs, and your trunk. So that's right. You need to develop the trunk and the legs in order to fire those, and that gives you greater stability.
so instead of trying to always chase stability, it's always good to create or to learn to have some internal stability within your body, um, right? So you can get better at doing these functional tasks, what have you, or
Yeah,
just
but again, I'd want to emphasize that again, if you're an elite athlete, you want to get stronger and more powerful. You don't need to sit on a Swiss ball or stand on a Swiss ball or a Bosu ball. Like I said before, we did another study with Mike Wall, one of my grad students, now a prof in our faculty of medicine, and we looked at elite athletes and looked at their muscle activation doing various types of activities, either under unstable conditions or under stable conditions, and there was no difference. And the reason for that was, again, they were elite athletes. So again, they already had really good stability. So having them stand on a Bosu ball didn't give them increased activation. They were already used to that because they were doing squats and deadlifts and Olympic lifts for years before that. So yeah, so elite athletes, you don't need to stand on a Swiss ball. Just, do the traditional lifts, Olympic lifts, or throw in unilateral. So single leg Bulgarian squats, things like that. Romanian squats on one leg, and that'll do the job for you.
did they? You said they didn't see increases in activation. Did they see decreases? I mean, if you get a professional and then put them on like something like a Bosu ball, would they see decreased activations if they were on the ground? Because eventually they won't be able to lift as heavy as they would. So
Well, again, like I said, we didn't see differences. Now, again, another article that we published years ago is that we looked at different degrees of instability. So when remember what I said, if you're moderately unstable, let's say you're standing on a Bosu ball, forces go down, but activation goes up because you need to activate those stabilizer muscles. But what we did is then we had them doing standing on like Swiss balls and different things that were even more unstable. When the instability was really high, everything dropped. So forces dropped, but activation also dropped. So there's, moderate instability will increase activation, but extreme instability will also decrease activation and decrease force. So
and
nobody wants to be too unstable when they're training. But if you want to be unstable, like the person who wants to do less weight, then be moderately unstable. Don't go to extremes.
that makes sense. So I guess moving on from that, I think we can start getting into a little bit of stretching, which is one of your expertise, I believe. Um, Regarding stretching, well, first of all, what is stretching and what are different types of stretches? Because I know
Yeah, well, of
there's
course,
variety.
stretching. Yeah, so stretching is trying to elongate the muscle, allow the joint to go through a full range of motion, and hopefully increase that range of motion after you're doing your stretching. And obviously, there's a variety of different ways of doing it. Traditionally, static stretching was the most popular. So you take your limb, whether it's your leg or your arm or your shoulder, and then you push it towards its maximum range of motion. Then you hold it there for a prolonged period of time. Might be, according to a couple of researchers, Judge and Eben, professionals, athletes that they looked at typically only stretch for like 12 to 17 seconds. What we found, and then in the late 1990s and early 2000s, there is reports that static stretching will impair performance. Well, we did more work on that, as did others, and we and others found that 60 seconds is kind of the magic number. If you do a static stretch that's more than 60 seconds without adding like dynamic stretching and dynamic activities, then you probably will get impairments. But if you do like, 2 sets of 20 seconds each or 3 sets of 20 seconds each, and then add dynamic activities, dynamic stretching, you're probably not going to get those impairments. We've also found that with what's called PNF stretching, proprioceptive neuromuscular facilitation. That's where you would go to, let's say, the end of the range of motion and hold it there for 5 or 10 seconds. Then you contract against either a band or your partner for 5 seconds or so, and then you go to a more extreme range of motion. Again, we did find if you did that for too long a period of time, again, you could have impairments. So you need to do a shorter period. Again, 60 seconds seems to be the magic number per muscle group. And then you've got dynamic stretching. Well, the problem with static stretching is that if you hold something for a prolonged period of time, the stretch receptors tend to down-regulate. They get less excitable. So your whole system is less excitable. If I want to fully activate my muscles, I want to be excited. I want my central nervous system to get excited, send down strong signals, inhibit the inhibitors, and I get full activation. But if I go and I stretch, let's say, my hamstrings for 5 minutes, and I'm holding them for a minute each, then these things called nuclear bag and nuclear chain fibers, they're part of your stretch receptors in your muscle. They lower their firing frequency, they lower their excitation, and so your whole system gets depressed, and that could be contributing to the impairments. So dynamic stretching is to have the limb move through a full range of motion, but of course dynamically. And if we do that, then of course those stretch receptors are going to get excited because now they're experiencing changes in length, changes in speed, and that sends excitatory signals back to the central nervous system. And so if you combine static stretching and dynamic stretching, then they counterbalance each other out and you don't get those impairments. But what we found in some of the meta-analyses that we've done is that if you do a single bout of stretching, then dynamic stretching, static stretching, and PNF stretching provide you with kind of similar increases in range of motion. But if you're going to stretch for the next 6 months, let's say, 2 or 3 times a week, then static and PNF tend to do better than dynamic stretching in terms of increasing range of motion.
So in terms of like acute range of motion changes, all of them seem to be effective equally. But if you're trying to just get better range of motion overall, like let's say maybe going for the splits or something like that, the static and PNF are likely better.
Exactly. And then, a lot of people these days are using foam rollers or rotor massagers. Same kind of message. We found that rotor massagers or foam rollers were just as effective as stretching in an acute. So you do one session of stretching, and whether it's static or it's foam rolling or whatever, you're still going to get a similar increased range of motion. But again, if you want to do 4 or 6 months or even 4 weeks or 8 weeks of flexibility training, static and PNF will be better than foam rolling. Foam rolling will still give you an increased range of motion, but not to the same extent as stretching.
Do you think there would be a need to do static stretching and then dynamic if you do static stretching under 60 seconds? Would they both result in the same benefit, or would you add dynamic?
I would still recommend doing dynamic in order to excite the system. But here's another. I'm sorry, here's another piece of information. You don't need, so let's say you're going to go and do your weight workout. So as you can see from all the wrinkles in my face, I'm a bit older than you are. So I've been weight training for 50 years. And for 50 years, I was told that, I should stretch and warm up before I lifted weights. But just recently, in the last couple of years, we just did a meta-analysis, and we found that resistance training, the caveat was not calisthenics, but either with free weights or machines or even Pilates will increase your range of motion similar to stretching. So you don't really need to stretch before you go work out on weights, because doing your chest press or your lat pull downs or your pullovers, etc., they go through a full range of motion with load added. So it's almost like doing dynamic stretching as well. So you don't really need to do static stretching before you work out on weights, but you're not going to do weights before you go play hockey or football or basketball or volleyball or tennis. So you still need to warm up. And so prior to competition, then you still want to do, and I would say, again, static stretching, there's some research that says it's more effective for preventing some kind of injuries, like explosive actions, than doing dynamic stretching. So I would still do a combination of static and dynamic stretching before I go and compete.
So even if static stretching doesn't reduce any excitatory drive, because if you do it longer than 60 seconds, it would, but if you do it before, it won't really affect it. But if you combine that with...
Sorry to interrupt. I was just going to say that's based on reviews and meta-analyses. So in general, 60 seconds is the magic number. But you can go and you can find articles, research articles, where they've done 30 seconds, 45 seconds, and some of those articles have shown deficits. So I'm saying, to be on the safe side, even though I've been saying 60 is the magic number, it's still possible that you might have some impairments, even doing 45 seconds. So why take the chance? Do a little bit of static stretching, try to increase range of motion, prevent injuries, add a small amount of dynamic stretching, and you'll be confident that you shouldn't have impairments.
And I mean, let's say there aren't any impairments, hypothetically speaking, before 60 seconds. Adding the dynamic side, even though they both result in the same range of motion acutely, the dynamic would still add the benefit of creating more excitatory drive to the system.
Exactly. Again, you get those stretch receptors, and all those nuclear bags and nuclear chains are firing off and sending reflex activity back to the central nervous system, and so then it decreases the threshold to activate some of those motor neurons and makes it easier for you to get fully activated.
So this kind of leads me to two questions following this. The first one being, if resistance training has been shown to cause similar range of motion benefits to the 3 different types of stretching that we've gone over, do you think in general people should, like, let's go 6 months, you want to increase range of motion, do you think people should stop stretching and just do resistance training with larger ranges of motion or full range of motion, or do you still think there's benefits to stretching outside of resistance training in general?
I would say that unless you're a hurdler, a gymnast, a figure skater, can't think about any others off the top of my head, but for the average individual who only needs an average range of motion, resistance training would do the job for you. But again, let's say you're a sprinter and you're driving your thigh up through a dynamic and explosive range of motion. You might want to do a bit of extra stretching in addition to your resistance training to make sure that you've got that sufficient range of motion to handle. Because static stretching also can increase the force output at longer muscle lengths. And so where do you get those typical hamstring injuries and groin injuries? It's at longer muscle lengths because the force length relationship of muscle. At longer muscle lengths, you exert less force. And so now, because of that, you're more susceptible to injury. So add the resistance trainings to make yourself stronger through that typical range of motion that you'll do when you're resistance training. Add this static stretching, again, if you're a big sprinter, hurdler, etc., to make sure that you've got that added protection.
Well, I mean, before we get into that, because I think that's one of the benefits or physiological benefits of stretching, I did want to ask, sometimes, I mean, even with weight training, when you do a full range of motion, you can kind of just static stretch with load, and that would still be a static stretch and just be heavier weight, and you're just loading the system more in that static stretch. But I would ask, do you think the studies that shown similar benefits with resistance training and stretching, how I think it's important to kind of point out how intense was that static stretching? Because sometimes, at least the studies that I've seen, showed it was like moderately intense or low intensity static stretching with resistance training. But how would that change with really high intensity static stretching with resistance training? Maybe static stretching could be better for range of motion increases.
Well, from the studies that I've seen, typically you either go to the initial point of discomfort or the maximum point of discomfort, and most of the studies typically go to the maximum point of discomfort. So I don't think you're going to see much of a difference. Whether in again, for the average individual, whether you're pushing yourself to maximum or near maximum, you're still going to get that increase in range of motion.
And how you mentioned with like athletes, like as gymnasts or ice skaters, you said that I also kind of wanted to add something I was thinking about. I mean, I do gymnastics myself, and sometimes when we'd stretch, they'd have us do, if we understand that 60 seconds is the general rule of thumb to like prevent any decreases in excitatory drive. For, let's say we're stretching the hamstrings, we could do a few sets of 30 seconds, anything below 60 seconds to prevent any calmness in the system. However, what if we go ahead and we do the split to stretch the hamstrings, but then we do another exercise to stretch another muscle, but it also stretches the hamstrings because the lower limb muscles kind of are all connected in some sort of way when we do a movement. So we do the splits to stretch the hamstrings, and then we try to stretch another muscle, but that stretch also just happens to stretch the hamstrings. Do you think a combination of these different stretches, and when trying to stretch different muscles, they also stretch other muscles the same? So maybe too much of these different variety of stretches can start to cause some reduction in excitatory drive, if that makes sense.
Yeah, it does make sense, and that's a great point, great question. We haven't looked at that because typically you look at one muscle group and you stretch them and you see what happens. So that goes again back to my recommendation that, even if you're doing less than 60 seconds, you should add dynamic stretching to excite the system afterwards, because, like you say, you may inadvertently be stretching your hamstrings 2 or 3 times from different types of stretching. So yeah, always add that dynamic stretching to subsequently excite the system.
Okay, so now that we understand that stretching, does cause increases in range of motion, and it seems that static stretching probably, or static stretching and PNF stretching, maybe increasing range of motion for weight training, may cause the best benefits for increasing range of motion of muscle. What is the physiology behind that? What kind of happens acutely when we stretch that can increase range of motion? And then what begins to happen more long term or chronically as we stretch when we increase range of motion, that benefits that stay there rather than reset?
Yeah. So we're talking about elastic versus plastic changes. So elastic means short-term changes. Again, as you say, if we do an acute or one session of stretching, what happens? For the most part, with one session, according to a researcher named Magnuson, and he was the first one, and so a number of us have also concurred, is that you get an increase in pain tolerance. So let's say I stretch and I'm trying to reach down to my toes, and it's not very comfortable, a little bit of pain. And so I'm trying to hold it and hold it. What you'll find over, a short period of time, again, 30, 45 seconds, 60 seconds, is that discomfort will decrease. And so what's happening is that your body is getting accustomed to that length. And psychologically, you're deciding, well, this isn't going to hurt me, so I can go a little farther. Physiologically, there's a couple of theories. There's the gate control theory of pain. So when I'm stretching, I can send signals back that are traveling faster than the pain signals, and I can block those signals. And then without the pain or discomfort, I can reach farther. There's also a theory called the diffuse noxious inhibitory control. And all that means is when I feel pain, I send that information up to my brain, and it'll release pain modulating substances like endorphins and enkephalins. They act like morphine and will decrease the pain throughout my body. So in the short term, it seems that pain tolerance or pain stretch tolerance is one of the main factors. Another factor that's important is the fancy word thixotropic effects. So thixotropic effects can be easily explained by ketchup. So take a bottle of ketchup and then turn it upside down, take off the cap, and see if the ketchup comes out. Ketchup normally won't come out at first. Now turn it back upside down, shake the ketchup, and then turn it upside down, and the ketchup comes out. What you did was when you didn't shake it, then the ketchup had high viscosity. It didn't want to move. Once you put a stress on it by shaking it, or what you can also do, you could have warmed it up, put it in the microwave or whatever, and then took it out, and then it comes out quickly. So the viscosity decreased either with heat or with stress. So whether I'm doing static stretching, dynamic stretching, or PNF, I can decrease the viscosity of the fluids in my tissue, which makes it easier for me to go through a full range of motion. So that would be the two major things that would happen with acute stretching. So that would cause elastic changes. So now you're going to stretch for 2, 3, 4, 6 months. And what's going to happen? Well, still, you're going to get a change in your pain tolerance. You can handle more pain. Every time you stretch, you're going to get a change in thixotropic or viscoelasticity. But then you're also going to get a change in stiffness. And so now the myofilaments tighten. There's a tighten protein inside the sarcomere. A number of different components will be less stiff. There'll be more compliance. And so, and one might argue, although there's not a lot of research to combine this, but it is in animals, you get what's called sarcomerogenesis. You add sarcomeres to make your muscle longer. So these factors would help to give you these plastic changes, so long-term or semi-permanent changes.
So regarding this idea of sarcomerogenesis, where you kind of brought it up a little bit before, to prevent injuries, which can shift that force length relationship, because as you add these contractile proteins, the length tension relationship where we generate the highest force can shift to these longer ranges. Do you think that is something that happens during, like, let's say a healthy individuals with normal joint excursions or range of motion? Because I find it that it likely more happens in like people coming back from bed rest or injuries or something like that, where it's, if they stretch, they're more likely to see these changes. And then in healthy muscles, it's unlikely unless they do something really extreme, like let's say they're trying to go for a split, then they might have to add these sarcomeres to get to those ranges.
Yeah, I completely agree. So like you say, if you've got a good functional range of motion, you would need to do something extreme in order to start adding sarcomeres. Whereas the injured individual who's been in a cast for 6 weeks and their muscles shortened because of that, now they're going back and trying to get that full range of motion, then they will be adding sarcomeres because they lost sarcomeres. So for the average individual, like I said, most of the studies that show increase in sarcomeres or sarcomerogenesis are animal studies where they hold muscles in a stretch position for days or weeks. Obviously, we're not going to do that in humans. So it's less likely we'll see that. but we'll see changes, for instance, in the angle of the uh, of the of the fibers, and again, in the compliance of the fibers in the average human doing stretching.
So, I mean, yeah, that's another point. I think with some of these studies, they have people in casts for like hours on end stretching at like high intensities versus you go to the gym or you probably do some yoga, you just hold stretches for a few seconds short term. So I don't think that's enough to really stimulate that. But I
Hmm.
mean, with resistance training, I think it's possible if we're constantly trying to generate forces at long lengths, do you think the body might adjust, let's say, to that? Um,
Yeah, there's another great question. I guess that's why you're such a good podcaster. So, yeah, you would expect that with resistance training, you've got a load. And if you go through the full range of motion and then hold it at that full range of motion, there'd be a greater chance that you might see increases in sarcomeres. But that's a great question. Nobody's ever looked at that. The problem is that it's hard to measure. You have to start doing muscle biopsies, and then if we do a muscle biopsy, uh, am I in the exact same spot I was before? How do I measure a whole muscle? In fact, with a muscle biopsy, you can't do that. So it's really it would be very difficult to actually measure increases in sarcomeres.
and I mean, a lot of the evidence is indirect, right? So I know some argue that the changes in the torque changes or shifts in the torque angle curves of the length tension relationship indicates that, but I've also been mentioned that that's also indirect evidence because that could be just changes in compliance of the tendons or something like that that can cause those acute changes.
Yeah, that's right. Yeah, so there's a number of factors that could contribute to that.
Okay, so it seems that acutely the changes that occur are more so from the neuromuscular system, and morphologically or uh, long term or chronically, it's more so morphological changes. Is there any other morphological changes that can occur other than adding sarcomeres in series, or is that kind of just the main change in muscle?
Well, like I said, the entire system can become more compliant. The type of proteins that are made. So, for example, again, going back to an example right now, I'm guessing you're in your 20s, I'm in my 60s. We look at each other and you're seeing wrinkles in my face, and I don't see too many wrinkles in your face. Why do I have wrinkles? Well, my tissue is made up of various proteins, collagen, and an important one is called elastin. So you can tell by the name that elastin is a protein that's elastic. As you get older, you lose elastin. When you've got more collagen to elastin, then your tissues are less elastic. So I have wrinkles because I have less elastin. An interesting not experiment, an example I do in my class is, have you ever done, so you take your hand, and you can try it here right now. So you squeeze the skin on top of your hand and let it go and see how long it takes for it to come down. So I just saw you, it's like immediate, right? Now watch mine. Mine took like 2 seconds to come down. Yours came down in like 100 milliseconds. So even with my hand, I don't have the elasticity that you have. So now let's go to my tendons and my muscle, and I'm not going to have the elasticity of a young person. But if I'm stretching, I'm doing resistance training, I'm promoting protein synthesis, and the protein synthesis is not just going to be actin and myosin. I'm probably going to be improving the elastin component as well and making my muscles more elastic over time.
I mean, that's a very cool example. I haven't heard that one before.
Mm-hmm.
Uh, so with stretching, then when we, I also wanted to ask something that I was looking into. I've also heard reductions in, I think they were H waves or H reflexes and T reflexes, if you're familiar with that. Even though I think they're acutely too. I think they come back like within an hour after you stretch or something like that. Maybe
Yeah.
if you can elaborate on what they are and
Sure.
how they kind
So,
of increase.
yeah, so an H reflex, H stands for Hoffman, the guy who found it, and it indicates the excitability, the afferent excitability of the motor neuron. So what you do with an H reflex is you send an appropriate stimuli onto the nerve. It goes back to the spinal cord and then comes back to your muscle, and then you measure the reflex response with EMG. And so again, what's it showing is that if you have a decreased Hoffman reflex or H reflex, that means that those muscle spindles I talked about before, they're less excitable after stretching. So when you send the reflex around, that twitch is smaller because you've got less excitability. So you can have, like we said before, to contract your muscles, you send a signal from your brain and it's excitatory, but then there's all these other inhibitory components that will, your ability to fully activate a muscle is like a balance between the excitatory and the inhibitory. And we want to decrease the inhibitory so the excitatory has a bigger component. If you're stretching for a long period of time, like we said before, the muscle spindles get less excitable. If you measure it with an H reflex, then you see the H reflex go down. The T reflex is just a, rather than do it with electrical stimulation, if you did that thing that doctors do to you and they hit your patellar tendon with a hammer, that would be part of your T reflex, tendon reflex. And so now you're physically causing your muscle to stretch. And then what we'd see is that reflex to go down as well from prolonged stretching.
That was really interesting. And those are just acute too, right? Those come back to baseline. So moving on from stretching, this also, well, actually, I guess this is still related to stretching. I know a lot of people stretch post-workout. We talked about it prior to workout, but they do post-workout to cool down because they believe it improves recovery or reduces delayed onset and muscle soreness. Are you familiar with the research on how confident we can be to say that it does do that, or if it doesn't really impact recovery?
No, it doesn't impact. So what will happen if you've got DOMS, delayed onset muscle soreness, and so 24, 48 hours later you stretch, you will feel better while you stretch. There's this thing called exercise-induced hypoalgesia. So if you've got some pain in your muscle and you go and exercise, so for instance, I've got arthritis, but when I go play hockey, when I first get on the ice, I'm not feeling very good. But after I warm up and I'm playing for a while, the pain goes away. So again, the system is masking that pain. It's hypoalgesia. And again, going back, gate control theory, diffuse noxious inhibitory control with endorphins, et cetera, these things are playing, the pain goes down. So getting back, I stretch, I have DOMS, it'll go down for the period that I'm stretching. But other than that, it doesn't do anything from the research in terms of decreasing either the pain, or the performance decrement, because normally with DOMS, you're also going to be weaker or less powerful. However, what we have found in some of our research and others is that foam rollers do tend to decrease DOM effects. And so the foam rollers, of course, DOMS is primarily due to inflammation in the affected muscle, and the DOMS seems to alleviate some of that inflammation and will help you to recover faster.
So with stretching, it doesn't make you feel better with if you have soreness and you stretch or passively stretch. It doesn't make you feel better like if you start playing hockey or something where that pain goes away, and it also doesn't speed up the recovery for soreness. But foam rolling does. I saw some. I know there's still some ideas on this, but I also saw that foam rolling doesn't really impact recovery, or you said it does.
Yeah, well, we've done a meta-analysis on it and looking. So again, this is what confuses people about science in general. You know, you're in the States.
Yeah.
I'm guessing. Okay, so you can have RFK Kennedy come up and say, "Oh, there's research showing that uh, vaccinations cause autism." You can find a research study for almost anything in the world, and that's why we do meta-analyses. Because what we want to find, we don't want to find one study. Because I often have students say to me, "Oh, this study proves blah blah blah," and I immediately say to them, "No, one study proves nothing. What you need to do is you need a body of evidence." And so, here I am, Dr. Behm, I have 30 more plus years of research. I do a study, and they say, "Well, geez, Behm done a lot of stretching studies. He must know what he's doing." Well, maybe I only had 12 people in my study, and 6 of those people, don't react the same way as the average population. Or maybe I looked at old people, and then people are saying, "Well, that applies to everybody." Or, again, I did 15 seconds of stretching, or I did 2 hours of stretching, or no, we need a body of evidence. And so that's why we do these meta-analyses. And so, yeah, you can find studies that show that stretching will improve DOMS effects or impairments. But if you look at 60 or 100 or 150 studies, then the tendency over all those studies is that stretching tends not to positively affect DOMS. And again, in terms of foam rolling, the 50 or 60 studies, or how many studies, maybe it's not 50 or 60, but the body of evidence with with foam rolling tends, I'm emphasizing tends, to show that you have a decrease in DOM effects or DOM impairments.
So with foam rolling, it seems like you get the best of both worlds. It reduces the pain sense, but it also actually does improve recovery. Do you know how it might do that? Is there any physiological explanation to why it does that, improves recovery and reduces the pain immediately?
Well, again, like I said before, so if we're rolling, we're pushing the fluids out of the muscle, so we can help to decrease the inflammation. And that's the major cause, the major factor of delayed onset muscle soreness. Just to throw out there for people who don't have an exercise science background, it's not lactic acid. Lactic acid only has a half-life or half recovery time of 15 to 25 minutes. So in 15 to 25 minutes, if you just exercise, half of all your lactic acid is gone. So most of your lactic acid is gone in 90 minutes. You only got 5% of the lactic acid left after 90 minutes. So 24 hours or 48 hours afterwards, lactic acid is not going to cause DOMS. So it's inflammation for the most part, and tissue damage is going to, and of course the inflammation is due to tissue damage. So that's what's causing the DOMS. So the foam roller is more effective, it seems, at alleviating some of that inflammation and pushing that tissue away from that muscle. Again, remember before we talked about thixotropic effects. So now I have inflammation, I'm stiff. So what can happen is that putting a stress on the muscle, that's going to cause a decrease in viscoelasticity. So I'll have a greater range of motion. And then again, if I'm doing it, so I'm pushing hard enough that's a bit uncomfortable, we go back to those pain modulating effects of gait control and endorphins.
Yeah, because inflammation, believe it or not, can be very painful, right?
Absolutely.
That doesn't mean it's bad per se. I think in context it can be a good thing, but I think in this case it is.
And everything that happens to us in a certain sense is good. So if I've got a sprained ankle and my ankle swells right up, the body is telling me, don't run on that ankle. The body is providing you with its own cast so that you can't move your ankle. And so then you're not going to further damage it. But the body, one might say, is very conservative. It doesn't want you to come back very quickly. So you're an elite athlete and you've got a sprained ankle and you've got a big game next week. Well, the body wants you to sit around and do nothing for 2 or 3 weeks to really have a good recovery. But if your team needs you a week or 10 days later, maybe you don't need as much inflammation or for it to last as long. And so now what you can do is, attempt to decrease some of that inflammation over a period of time, and allow you to get through do some stretching exercises, some low load strengthening exercises, and you can recover faster than nature would typically allow you to do. So yeah, inflammation is important, but we can accelerate the process with modern science and medicine.
And with inflammation doesn't it have any benefits or nutrients while it's still there? Like it's also healing of some sort?
Yeah, well, the inflammation is because your immune system is going down there. So what you do is you release what are called cytokines. So again, let's say you sprained your ankle, and there's damage to your tendons. They're going to release these cytokines, which are messengers, and they'll go up and tell the body that there's an injury in your ankle. So then the immune system is then attracted to that area. That's why you get a swollen ankle. You don't get a swollen neck, because the cytokines are attracting the inflammation down, and the immune system down to your ankle. And then the immune system with the T cells, with the macro, I'm trying to remember the proper names. You got natural killer cells, macrocytes, lymphocytes, leukocytes, all these sites. They're going down there, and they're eating up the dead tissue and the damaged tissue and trying to clear out that area. And so, they need time to do that. So obviously, we, like you said, inflammation is good because it's down there trying to repair the tissue. And like I said, that's great, but we can accelerate that process somewhat.
But sometimes when people try to accelerate it too much, it could impair some of the recovery. They could perform immediately.
That's right. People try to come back too quickly, and the tissue is still not fully recovered, and you damage it again. So so it's a delicate interplay between how fast we can accelerate the recovery process, but it's dependent on the individual and their prior status and the extent of injury. There's a lot of factors involved.
Now, I did want to come back because I did forget to mention this with the foam roller. Going a little back on how the foam roller can improve acute changes in range of motion. It doesn't decrease excitatory drive, right?
It doesn't seem to. I'm just trying to think, because we did do an experiment with the H reflex and post rolling. That was quite a few years ago. From the top of my head, I'd have to look it up again, but I don't think there was a decrease in the H reflex with the roll.
So it kind of it's like putting in an input on your body. This is mechanical input of the foam roller. It just creates pressure changes or fluid changes, and with that just create a different mechanical output from the body, allowing you to have some acute changes in range of motion.
Yeah, exactly.
Okay, perfect. So I know we are running a little bit out of time, but I did want to finish talking about fatigue. I know you've done some work on fatigue, or quite a bit of work on fatigue, I think.
I've done a bunch of stuff.
About before we get into perception of time and how fatigue can affect on someone's perception. First of all, what is fatigue, if you could kind of like simply define it? And is there, in terms of resistance training, is there differences in fatigue between low and high reps, if it's more contraction specific per se?
Sure. So a common definition of fatigue is a decrease in force output, torque output, power output, but that's not a complete definition, because, for example, let's say I just saw you taking a drink of water there. Let's say I took that bottle and I held it out, and I could hold that bottle with my arm straight for a long period of time, and I'm not dropping the bottle. So you might say, well, there's no fatigue there because he hasn't dropped the bottle. but the sensation in my shoulder could be increasing and telling me, oh, this bottle feels like it's getting heavier and heavier and heavier all the time. So even though I haven't seemingly lost force or torque output, the sensation of that of sustaining that bottle or any kind of load is increasing, and psychologically I'm having to, well, not psychologically, physiologically as well, as my fast twitch fibers de-recruit, I have to recruit more fibers, but you don't see it externally. So it's not only just a loss of force output, but it's the, the effort and the perception of effort can also be part of the fatigue process. So then you're asking about high load versus low load resistance training. And so, one's endurance and one is for strength. And so what we typically see, for example, would be if we're doing something like a low load, either dynamic or even isometric for a long period of time, we probably see a lot of metabolic changes. So, my ATP may be running low. I may be experiencing more acidity. I'm generating more hydrogen ions, which contributes to acidity. So I'm making more lactate to buffer that acidity. So a lot of metabolic things can be going on. But with short term, we're probably not going to see as much changes in metabolic, but we're going to see changes in neural responses. So again, if I'm lifting something really heavy, my fast twitch fibers have to be recruited. And then in a short period of time, because they are highly fatigable, they are de-recruited. And then I have to try and recruit other fibers to balance those out. So in general, high loads have a greater predominance of neural responses in terms of fatigue, and lower loads have a greater response, greater contribution of metabolic alterations.
So it's always kind of commonly stated that low loads cause more CNS fatigue than high loads, but we have seen research showing that high loads do seem to cause pretty high degrees of CNS fatigue, probably due to generating force for longer periods of time. Would you agree with that statement, or is it just not as simple as black and white? Low loads cause more CNS, high loads cause more metabolic.
Yeah, no, of course not. It's never simple. So, like I said, low loads would have a greater metabolic effect. But what does that metabolic effect do? Well, of course, the lactates and the acidity would be detected by the system, and as you're generating more acidity and lactate and hydrogen ions and CO2, potassium, they're circulating through the system and getting into the central nervous system. And then your system is being informed that forces are decreasing, or like I said before, the sensation or efforts increasing, and therefore there's changes in the central nervous system. So yeah, they both have changes in the central nervous system. It's just that the low loads, the central nervous system is detecting what's happening to the changing in metabolism, whereas the high loads, because it's normally a very short duration, it's a more direct effect on the central nervous system.
Yeah, I think what would confuse people is that when you do high reps, you get like a pump. And so that feels like there's more metabolite related fatigue. And so I think that's what causes some people to say, oh, well, high loads cause more metabolite related fatigue, low loads cause more central nervous system fatigue.
Yeah, it would be generally the opposite.
So with that fatigue, then, do you think there's also this, how you mentioned with the bottle squeezing, about this perception of effort? I know there is I don't know if you heard of this model, but there is a model, the psychobiological model of fatigue, where they talk about the perception of effort, but only in endurance training, where they're like, well, what really fatigues first is your brain rather than the actual muscle or the metabolic products that reduces or inhibits your muscles. And they suggest, well, you fatigue or you stop performing the task because your brain fatigues first. Your psychologically, your perception of effort gets too high and you can't do it anymore.
Yeah.
But in terms of resistance training, I always wondered how that would apply to that. I mean, if if we're lifting really heavy loads, do we fail because of our perception of effort or generally because our muscles give out? But maybe with high loads, there is this increase in perception of effort, which is more related to squeezing the water bottle, where it's easy at first, but then it gets harder. Maybe that has more application to the perception of effort being cause of fatigue rather than actual metabolites or something like that.
Yeah. So, two quite famous researchers, Noakes and St. Clair Gibson, they did a lot of work on pacing. And that was with mostly with endurance athletes. So as you know, if you're going to go run a 10K race, the good runners typically sprint at the start to get ahead of the slow runners. Then they go down and they have a pace that they keep for the next 9 kilometers or so. And then the last kilometer, they pick it up. So they've paced themselves and then they can sprint at the end. And you can tell people to run as hard as you can. And if you tell them, I want you to run as hard as you can until failure, for a kilometer or 5 kilometers, they can't do it. The body will not allow them to do it. What we did is we did a series of experiments as well. And we thought, okay, well, endurance training, they're going to be running, let's say, again, 5-kilometer race, a good time would be 20 minutes. They're not going to be able to do maximum effort for 20 minutes. But we thought, okay, what if we do isometric contractions and we tell people to do maximum contractions? And we tell them, okay, let's do 12 maximum contractions. So we test them to start off with, let's do 1. So let's say they did 1 and they got up to, 100 newtons, just a nice, easy round number. Then what we told them, okay, that was 1 maximum contraction. Now what we want you to do is we want you to do 12 maximum contractions. Each one has to be maximum. And the first contraction is never 100 newtons. They're usually down at 90 or 92. They think that they're going to do a maximum contraction. They want to do a maximum contraction, but they can't do a maximum contraction because their system knows that they have to do 12. And so we're going back and we're worried that we're going to get attacked by a saber-toothed tiger. And so what we want to do is we want to save some energy to run away from the saber-toothed tiger. And so what we found was when we told them to do 12, they dropped down to, again, I'm just making up these numbers, but they dropped down, let's say 90 newtons. And then, of course, they got fatigued and it went down. When we told them, okay, that's number 11, you got one left, boom, forces went up. They did not push themselves as hard as they could, even though they thought they were doing maximum. Then what we did, another experiment, is we said, okay, we want you to do 6 contractions. And then they'd come back another time, I want you to do 12. The third time they came back, we said, we want you just to do as many as you can. We'll tell you when to stop. Well, when we told them to do 6, then the drop, again, if they did 100 newtons with 1, maybe they only dropped to 95 rather than 90 now when you did 12. But there was still a drop because they knew they had to do 6 and they had to reserve some energy. But when we told them, okay, you just do as many as you can, they really dropped. And again, we said maximum, do maximum. They tried to do maximum, but when they did not know how many they were going to do, their body caused them to drop. So there's a strong psychobiological, as you called it, or psychological message from your system that you are going to conserve energy even when you think you're going to do maximum.
So that's actually very interesting because whenever you do a set, especially with high repetitions, let's say 20 to 30, it's kind of already mentally, I don't know if mentally exhausting is the perfect way of saying it, but if I have to do a set of 5 reps, I'm going to feel like a lot easier to just hop in and do that set even if it's heavyweight, rather than doing a set of 30 reps, because I know that it's going to get harder near the end. And it's just more mentally draining to think about doing a set of 30 reps than doing a set of 5 reps.
Mm-hmm. And a good example of that is that the term that we use is non-local muscle fatigue. So again, let's say I'm doing, I don't know, a 30-second isometric contraction of my elbow flexors. And then I ask the person to do a contraction with the contralateral elbow flexors. They will have impairments on the contralateral side, especially if I ask them to do an endurance type activity, because they've spent 30 seconds focusing on this right bicep, trying to contract as hard as they can. And then they're getting mentally fatigued trying to, keep that force up. Then I said to them, okay, this left bicep, you haven't done anything, so it shouldn't be tired. But when they try to exert forces, especially for a prolonged period of time, forces go down. So again, they got mentally fatigued doing the right bicep. And then when you asked to do the left bicep, they couldn't do as much.
Do you think fatigue has some sort of, well, first of all, I guess with high reps, then it's likely that it could be this perception that has a role in causing some limitations. I guess that when you train, that perception could also improve. But do you think fatigue also has some contraction specificities? For example, concentric contractions or eccentric contractions being more fatiguing, or isometric contractions being more fatiguing?
Oh, yeah, absolutely. With training specificity, the type of contraction you do will affect the type of fatigue that you experience. So, eccentric contractions are more damaging than concentric contractions. So again, going back to DOMs, you'll get more DOMs with predominantly eccentric contractions. So yeah, it's very specific to the type of activity you're doing. Again, we could also say about plyometrics or counter movement jumps or something like that. The type of fatigue would be specific to the type of action that you're doing.
I mean, concentrics are always brought up to be more metabolite related fatigue. The thing is, what I've noticed is that whenever you perform a concentric, you have greater sensation than when you perform an eccentric. So, I mean, so I think that causes people to believe that concentrics are more fatiguing because there's greater sensation. Uh, would you agree with that, or might you know where that sensation could be coming from, or the different sensation types between contractions?
Well, if you're doing a submaximal load, so let's say, like you said, I'm going to do 10 reps. You use less muscle fibers or more motor units to sustain the same load eccentrically. So again, let's just make up some numbers. Let's say that we are benching 100 pounds or 100 kilograms. And then I have, again, you have, like, for instance, in your bicep over about 250,000 muscle fibers, but let's just make up these fancy numbers and say you have 100 motor units. So if you're doing a concentric contraction, you're lifting 100 pounds and you have 100 motor units. Each motor unit only has to lift 1 pound. That's concentrically. When you go the eccentric, so you're bringing the weight down, the muscle doesn't fire as many motor units because the eccentric is more efficient. So again, I'm just going to make up these numbers just to make it easy. Let's say that you only turned on 50 motor units eccentrically. So now what you've got is you've got 2 pounds per motor unit on the way down. So you fired more muscle fibers concentrically, which would be harder for the central nervous system, to try and activate all those muscle fibers. You fired less on the way down. So the central nervous system, it's easier eccentrically, but for the muscle, it's harder because it has to sustain, in this imaginary story that I just made up, it has to sustain twice as much weight. So morphologically, eccentric, as we know, is harder. You run downhill. We have a race here in St. John's, Newfoundland, that's 10 miles long, 16 kilometers, and 2/3 of it's downhill. And you think, oh, that makes the race easy. Well, actually, people find it harder afterwards because it's so much eccentric contractions.
Mm. So, I mean, do you think concentric contractions cause more sensation because there's more activated motor units then?
That's right.
So, finishing off then, I'd like to finish off the podcast with the perception of time and fatigue. If you could kind of, summarize your work on that, what you were looking when you guys were researching this, and how could that impact practically some scenarios in resistance training in the gym, if that's all right.
Sure. Yeah. So, as you know, let's say you're going to do a plank, and you want to hold that plank for 1 minute. And so you're down, you're doing your plank. 30 seconds goes by, and you ask the person with the watch, is it 1 minute yet? and you can't believe it's only been 30 seconds. So time seems to go by faster when you're tired. Yeah, it's got to be 60 seconds. No, it's only 30 seconds. So your perception of time changes when you're doing exercise. And so we looked at high intensity versus low intensity exercise. We looked at older individuals, and we looked at sex differences. And yeah, we did find that with higher intensity work, that you felt like time went by faster. You thought that more time had gone by than actually had. This has a big impact again on sports that are time related. So in football, you only have typically 30 seconds from when they put the ball down to have your huddle and then get the play started. And so you've got to know how long, what is 30 seconds. You got to be able to feel that and estimate it. And if you're tired, you're going to think that 30 seconds has gone by faster than it is. Or you're a basketball player, depending on which league you play in, you might have 24 seconds from the time you bring the ball up till you have to shoot. In tennis, you've got 30 seconds from when you get the ball and you have to serve. So you might be handling that fine at the start of a game. You have a feeling how long 30 seconds is, but as you get tired, that perception is changed. And so when you're practicing, your athletes should be practicing when they're fatigued, so that they get a better understanding of how that time is affected.
That's really interesting. I mean, as someone who's been in PE class, we'd always have that plank holding competition, and 1 minute feels like
Forever.
3 minutes of some sort.
Yeah,
and you think, what do you think plays into that? Is it fatigue that causes that time dilation, or do you think there's other things internally?
Yeah, well, you have there's a couple of theories about how your brain works, and one of the theories says that the number of inputs into your brain determines how long you think something has passed. So, for example, people say, "Oh, geez, I'm bored. Time is going by so slowly right now." And you go, "Well, why would that be?" Well, when you're bored, you're probably not doing anything. So therefore, there's not many inputs. You're not reading, you're not on your computer, you're not exercising. So your brain's not receiving a lot of inputs. So it seems that time is moving really slowly. When you're doing your plank and you're holding that plank, your muscles are getting tired. And so there's a lot of sensory information going back to the brain, saying that, there's a lot of things happening. My trunk muscles are working, and my leg muscles are working, and I got my shoulders, my arms are all working. There's lots of inputs going back to the brain. So the brain says, oh, if there's lots of inputs, that must mean time is going by really fast. And that's why you think that 30 seconds is actually you think 30 seconds of plank is actually 60 seconds. You've got all these inputs going in. So you have to try and be able to, again, like we said, understand how many inputs actually equal. And when you're fatigued, you're getting more sensory input back, which makes you think the time has gone by faster.
Do you think practically this has any place in a resistance training setting?
Well, you could, when you're resistance training, do more like some people would call functional training, where you combine mental exercises while you're resistance training. So you could incorporate, and tell somebody to do, like I say, do a plank for 30 seconds, do your squats for 30 seconds. And while they're getting tired, they have to become more familiar with what 30 seconds is.
And that would help them prevent them from kind of like stopping the exercise before time is
That's
actually
right.
up.
Again, the quarterback, when he's tired or she's tired, they have experience of 30 seconds when they're fatigued. And in the weight room, they've been doing this. They've been doing squats, they've been doing bench press, and they've been doing that when they're fatigued for 30 seconds. And so now they understand, okay, when I'm fatigued, 30 seconds feels like this. compared at the start of the game when I'm not fatigued, 30 seconds feels like a longer period of time.
Yeah. And I mean that's it's a really cool experiment. I think everybody thinks of that whenever they're working on in the weight room. That's
Mhm.
probably why they don't like doing high reps, or they don't like doing planks for a minute, or anything that's struggling. Dr. Behm, thank you so much for your time. If people are more interested in learning more about your work, or uh, being more updated with you, if you're still very active in the field, do you know where they might be able to find you, or if you've written any books that they might be interested in reading?
Sure. Yeah. So if they want to find some of my articles, they can go to ResearchGate on the web and just punch in my name, and many of my articles are available there. You can go to Google Scholar, again, punch in my name. A lot of my articles are there. I wrote a book on stretching. It's the second edition is out, and you can get that either through Routledge, ROUTLEDGE publishers, or you can get it on Amazon. And so so they're all available.
And I'll make sure to have them I'll make sure to have the links for that below in the captions, for people who are interested in pursuing that. Again, Dr. Behm, thank you so much for your time, and I hope you guys enjoyed this episode, and I'll see you guys on the next one.
All right. Thank you very much for having me.